So good morning and welcome to our webinar Wednesday. Today's topic is 100% outside air systems with variable refrigerant technology. Dan is going to be our presenter. And if you have any questions throughout, go ahead and put them in the chat and then we'll answer them at the end. And if you are requesting PDH credits or the AIA cert, make sure that your name that's showing as under the participant panel is a name that I can link up with how you registered. So if it's something that doesn't make sense to me, I won't be able to give you that credit. So go ahead and make sure you update that. If you don't know how, you could just direct message me and tell me your name. So with that, Dan, I will hand it over to you.
Thank you, Kelly. Appreciate it. And good morning to everybody. Thank you for taking time today to join us for this webinar. We appreciate your time commitment and we'll do everything we can to make it relevant for you today. I'm trying to share my screen. And Kelly, do we have everything opening up properly?
Perfect. You're good to go.
Okay, thanks so much. Again, my name is Dan Hahne. Many of you have joined us in the past, so I won't labor an introduction anymore, other than to say that I've been in the industry since 1985, and my role at Varitec Solutions today is Director of High-Performance HVAC Systems and as the corporate educator. I've had the privilege of participating in a number of co-authored articles in the past on active chill beam systems and condensation issues, as well as the concept of designing to code minimum for healthcare facilities and why should we think beyond that. And this July, I had the privilege with ES Magazine to write their featured article, 100% outside air refrigerant systems, a sustainable hybrid approach for superior IEQ, a very important topic today with the various pressures we're seeing in our market. So if you want to have a document reference or an article reference for today's presentation, I suggest you go to ES Magazine's website and look for the July edition and you'll find the article. Who is Varitec? For those of you who may be joining us for the first time, we are an HVAC system solution resource. We've been in the industry for 45 years and have a marketing presence from San Diego through to Lubbock, Texas. And we can assist engineering and architectural teams on evaluating HVAC system concepts that might be appropriate depending on the type of building and the project that's being evaluated for design. We can assist with mixed air VAV systems, variable refrigerant systems, underfloor air systems, 100% outside air systems, et cetera, et cetera. And I'm pleased to say here in Phoenix, Arizona, we can actually look at a packaged central plant solution through Daikin's packaged central plant manufacturing facility here in Phoenix, Arizona. So we're pleased and proud of that capability. Our goal for the future is to help shape the future of HVAC designs. There are many pressures growing in the market that many of you are already aware of, and pressures that are looking for enhanced energy efficiency, which invites a reconsideration on how we do heating and ventilating designs. So our mission at Varitec is to provide an educational platform for educational learning in the HVAC industry with a focus on high performance buildings and innovative technologies for a better built environment. To assist us in those goals, we have launched in 2022 our Varitec Technical Institute's presentation seminar webinar series. We call it Webinar Wednesday. We actually began not with a webinar. We held a Varitec Sustainability Symposium on May 12th, where we had Chris Mathis and Dr. Edmundo Soltero of ASU be our featured keynote speakers on why buildings matter and how buildings are being designed, certainly at ASU's campuses, for the future, keeping the environment in mind. On June 15th, we had Bill Dietrich, product manager for Daikin Applied Chillers, on the future of refrigerants. And on July 14th, today, or it's actually 13th, I apologize for the typo, we have 100% outside air variable refrigerant systems, and then we're going to be looking at 100% outside air active and passive chill beam systems on September 8th. and October 13th, we're going to be looking at passive radiant heating and cooling systems. For today's presentation, I have to thank a number of individuals who supported this initiative. They have to, a special thanks to Eric Martin and Stephen Zhang of Smith Group for letting us look at a medical office building to evaluate for this study. For Daikin Comfort, we had Christopher So, their VRV product engineer, who helped us to optimize the VRV layout. We had Judy Peters, the energy modeler for Daikin Applied, assist in evaluating system concepts and design and energy consumption. And then, of course, we had Zach Niemeyer, our sales engineer, and Oster Vetter, the sales support engineer, to help design the systems that were under evaluation. So with that being said, let's begin with today's presentation. And we do have a lot of information to cover. So I'll be touching on many slides and hopefully covering salient features or points of each slide. So if you have any questions, please put them in the chat and we'll address them later. I want to make sure that we get through all the information today, and then the presentation will become available on our website, as Kelly pointed out to you earlier today. Today we're going to look at ASHRAE, the CDC, and the EPA, and agency statements on how do we improve indoor air quality and indoor environmental quality of buildings. We're going to look at IEQ and decarbonization and net zero and the consequent dilemma. We're going to look at spanning the divide of that dilemma with a proposal for 100% outside air system using variable refrigerant technology. We're going to explore variable refrigerant technology, a very quick overview of the system and why they achieve their efficiency levels. Then we're going to look at 100% outside air VRV, a system concept review. And then in line with the article that I mentioned earlier, we're going to do a comparative evaluation. We're going to do a comparative analysis and evaluation of 3 system concepts applied to a 28,000 square foot conceptual medical office building. We're going to look at equipment first costs and payback for those 3 system designs and offer some concluding remarks. So let's look at the various pressures that we're seeing today in the industry. We're going to look at ASHRAE, the CDC, and the EPA and understand what they're saying and why. On April 5th, 2021, ASHRAE's Epidemic Task Force issued this update. Airborne transmission of SARS-CoV-2 is significant. Consequently, ventilation and air conditioning systems can reduce airborne exposures. And an ASHRAE task force recommendation is to increase the outside air fraction rates from building design levels up to 100%. The Center for the Disease Control, the CDC, came out on May 7, 2021, saying SARS-CoV-2 is transmitted by exposure to infectious respiratory fluids, and that one of the 3 means of infection is the inhalation of air carrying very small droplets and aerosol particles that contain infectious virus. The CDC also offers recommendations when indoors, such as looking at ventilation mitigation strategies, and where possible, to even eliminate HVAC air recirculation. The Environmental Protection Agency, or the EPA, has issued this language. An important approach to lowering the concentrations of indoor air pollutants or contaminants, including any viruses, is to increase ventilation, or the amount of outdoor air coming into indoors, and ensuring that proper ventilation with outside air, in doing so, will help reduce the concentration of contaminants, including viruses. The EPA has also issued their Clean Air in Buildings Challenge, and its goal is to optimize fresh air ventilation to create better IAQ. And it offers also a fact sheet guideline on how to achieve that. And one of the line items is to run your HVAC system during all occupied hours to ensure clean air enters and is distributed throughout the building. Please be aware the EPA does monitor contaminants both of indoor air and of outdoor air quality. And it could very well be likely that the indoor air quality is worse in many buildings, certainly many older buildings, than the outdoor air condition. Of course, you have to take into consideration whether or not you're comparing the outdoor air of Los Angeles or even Phoenix on a February morning versus Flagstaff or Sholo, Arizona. Regardless, outdoor air quality can often be superior than indoor air quality, and certainly CO2 concentrations of the outdoor air are currently less than indoor air. So let us look at the challenge with these pressures that we have before us. Let's look at IEQ, net zero, and decarbonization, and the problem that this creates for design teams. So first of all, what is indoor environmental quality? It is not IAQ. The CDC defines indoor environmental quality as the quality of a building's environment related to the health of occupants, and it's based on the dampness of the indoor environment, its cleanliness, and the amount of ventilation in the environment. The USGBC defines IAQ as encompassing the conditions inside a building such as air quality, lighting, thermal conditions, ergonomics, and their effects on occupants and residents. So IEQ addresses the human element. It's not just a measuring of contaminants in the air. It actually helps to define what those contaminants or how those contaminants influence the human physiology. The EPA in 2010 released a document called their National Programs to Assess IEQ Effects of Building Materials and Products. And there is now a global alliance for IEQ that is formulated, that is pushing IEQ initiatives across the globe. There's also a whole building design guide that's advancing the initiatives and agenda of the IEQ. And they have pointed out quite clearly that IEQ can influence a company's productivity and consequently their performance bottom line. We also see the development of a new organization called Building for Health, or B4H, that was actually founded by Dr. Stephanie Taylor, a leading authority on IEQ and what needs to be achieved within a building in order to support improved personal health of occupants within those spaces. And the B4 Health team has developed a technology to actually monitor the IEQ of a building by creating a building health score. So you might be interested in looking at that, where a building owner might be able to achieve a dynamic read and score regarding the state of their current indoor quality and making sure that the systems are working to maintain that objective. So the dilemma. What about the energy burden to achieve all of these movements that are influencing the industry towards better IEQ? Well, we have the AIA 2030 commitment. It's a national movement among architects, among the AIA, so that the builder, making the observation that the built environment, our buildings, the world of our buildings, creates a staggering 40% of the world's CO2 emissions. And architects, engineers, and owners play a key role in that. And it made the statement that their objective is to commit to a net zero emission of carbon by 2030. The Carbon Leadership Forum has this position that all systems engineers shall advocate for and achieve net zero carbon in their projects. Operational carbon by 2030, that is to say the carbon released into the environment to maintain building conditions throughout its operation throughout the year. And then the embodied carbon, which is the carbon released to create and make the components that went into the making of the building. ASHRAE Standard 90.1 2019 has been recognized by the Department of Energy as the standard to be adopted by municipalities for future building codes so that they meet and conform to the enhanced efficiency that Standard 90.1 2019 offers 2016. The same ASHRAE journal that released that announcement of the DOE also had an article on how building decarbonization can transform HVAC systems. So there is a movement within the industry towards electrification and decarbonization. And that article addresses certain HVAC solutions that will lend themselves to achieving those objectives. And in the article, Peter Ramsey states that an all-electric building coupled with a renewable or carbon-free source of electricity is considered to be decarbonized in its operations, and it recognizes one viable solution for meeting that objective is heat pump technology using variable refrigerant flow. But again, in the meantime, we have the ASHRAE's Epidemic Task Force saying that to create better IEQ and better indoor air quality and reduce the risk of infection during the pandemic, we need minimum filtration requirements of MERV 13, MERV 14, ideally HEPA filtration, which is not really feasible, but it is optimal. Also, it advises that we increase outside air fraction rates up to 100% outside air where possible. And also to maintain building humidity levels between 40 to 60%. So there's a significant impact on operating costs to employ or utilize these strategies to reduce the risk of infection within the built environment. So in looking at these pressures, I thought maybe it'd be a good idea to explore if there's a solution to bridge the divide on an HVAC solution that will allow for better IEQ, better IAQ, but also offer optimal energy efficiency so a building owner in the end doesn't pay a premium, creating an environment that is conducive to human health, but perhaps maybe even save more money by adopting that system. So that was the purpose of the article, and it is this presentation today that we're going to review the findings of to help us assess if this is a good approach for future building designs that our industry can incorporate, certainly in the Southwest Desert. So spanning the divide, what are 100% outside air systems? The design intent of a 100% outside air system is to decouple the outside air or the ventilation load from the HVAC system. It is designed parallel to heating and cooling components. There are certain considerations on how a 100% outside air unit or DOAS unit is built. It incorporates heat recovery, where for the most part, or it can, or if you want to optimize efficiency, you would want to use heat recovery, where building exhaust air is used to precondition the outside air. And there are two ways you can do that. You can provide a heat recovery solution that handles the sensible load. That is the load that is the amount of energy in the space or building as measured at a thermostat, or enthalpy, which is the total load, which is comprised of the sensible load as well as the energy that holds water in a vapor state, otherwise known as humidity levels. So when you use a 100% outside air system, however, you have to make sure that you're exhausting as much air from the building as outside air is supplied, so you maintain a positive building pressure of 0.01 inches. So if you're going to exhaust that much air, why don't we focus that into an exhaust air stream that can be used with a heat recovery solution so the outside air can be preconditioned before it hits the cooling coil. So the design consideration of a 100% outside air unit is a little different, excuse me, from conventional air handling units or package DX configurations. So what are the outside air advantages? Well, you can control the outside air rate to each zone. That is to say, there's no question about outside air hopefully mixing at the appropriate ratios within the return air and is consequently uniformly distributed throughout a building. You can provide the outside air required for each zone directly into the zone. And consequently, you have deeper control of your outside air, and you're not necessarily limited to designing to code minimum as defined by ASHRAE 62.1. In fact, ASHRAE in its Epidemic Task Force guidelines recommends designing outside air volumes at rates greater than the minimum to reduce the risk of infection. You can provide deeper CO2 control. There's evidence that high concentrations of CO2 within a building might be a human health concern if you start seeing levels of 1,000 parts per million or above. So there's a current consideration and debate going on as to what those CO2 levels can be. But since the CO2 levels outdoor are below what they are indoors, we can help control CO2 levels more effectively. You can actually provide humidity control by providing lower dew point supply air. We can add enhanced system efficiency by incorporating the heat recovery solution that we discussed earlier. And in doing so, you can then downsize the variable refrigerant system that offers many various advantages. So what, first of all, is a variable refrigerant volume system? What is the technology? What are we doing? First of all, let's just quickly reevaluate what an HVAC system is trying to do, because we have many guests joining us today who are not engineers. The first goal of an HVAC system is to maintain occupant thermal comfort needs. It is also meant to create healthy built environments. And we help create healthy building environments by controlling humidity to the appropriate RH factor in the building to reduce the risk of infection and to maintain human health. What is energy efficiency? The Department of Energy defines energy efficiency as the use of less energy to perform the same task or work or produce the same result, So reducing the amount of energy consumed in a building to allow for the same objective of maintaining thermal comfort and creating healthier buildings is the purpose of energy efficiency. ASHRAE's Standard 189.1 is their high-performance building design guideline, and it embraces the holistic approach of designing HVAC systems so that they are capable of being operated in a manner that increases environmental performance and economic value over time, and seeks to establish an indoor environment that supports the health of occupants and enhances satisfaction and productivity of occupants, and maintain energy efficient systems. So if you're looking at securing both objectives for a building of improving IEQ as well as system efficiency, ASHRAE Standard 189.1 would be a standard you would want to probably look at. So effectively, a high-performance building achieves the objectives of an HVAC system while only consuming that amount of energy necessary to meet that demand, to meet that load at any given time of day and at any given time of year. A conventional HVAC system, a conventional mixed air system, to maintain thermal comfort in cooling effectively results in this. And let's just clear the table. It is this simple. An HVAC system controls the built environment by either removing energy in a building that it acquires during the day and depositing it outdoors when it's in cooling and dehumidification mode, or it's adding energy in the winter months when it's heating and or humidifying, which, by the way, the winter months are our driest times of year. In a conventional mixed air system, the heat transfer media, that is to say, what we use to move energy from the building to outdoors, is air. Air carries energy from inside a building to an air handling unit coil, where that air is conditioned, brought to a lower temperature. The energy in the air is stripped at the cooling coil and taken to either a condenser or a chill water loop, so that heat energy can be deposited outdoors. The problem is that air is not a very dense heat transfer medium. It requires a lot of air to move the energy gained during the day, either sensible energy, which is the measure of energy in a space as read by a thermostat, or latent energy, which is the amount of energy necessary to hold water in a vapor or gaseous state. Air can only hold 0.46 BTUs of energy per pound of air. So you need a lot of air to move the energy gained in a space during cooling mode to deposit it effectively outside so you can maintain building conditions. I've been an advocate of chill beam systems for years. And the reason why chill beam systems are energy efficient is because water is the heat transfer medium for a building's sensible load. Water is a denser heat transfer medium, and it can hold 8.98 BTUs of energy per pound of water. So you need a lot less water to move the same amount of energy than you do air. Consequently, you have less system horsepower. Well, let's look at refrigerant. Refrigerant is an even more dense heat transfer medium. Refrigerant can hold 88.2 BTUs per pound of refrigerant. Consequently, you can move an awful lot more energy with a lot less refrigerant than you can either with water or for air. So these systems invite every consideration as an energy efficient heat transfer solution. So when we apply variable refrigerant technology to a building, what actually is it? You might be asking the question, how does it work? Well, first of all, it is a split DX refrigerant system. That is to say, the condensers that deposit the heat gain in the refrigerant gained within the building is deposited outdoors. That's the unit that actually dumps the heat energy secured by the refrigerant from the building and deposited outdoors. The indoor air handlers that offer the ventilation and the cooling coils are indoors, local to each zone. The package DX rooftop unit actually handles the total cooling load, both sensible load and latent load, at the cooling coil within the rooftop unit and uses air to transfer energy from a building. Variable refrigerant brings the refrigerant down to the building zone, so it's local to the space. The condensers used in a variable refrigerant technology are variable speed. So instead of on-off cycling, they actually effectively ride a building load. They can deliver only that amount of refrigerant necessary to cool or heat a space, as opposed to cycling compressors that result in a high current inrush when you go through a start-stop cycle in a conventional DX unit. Consequently, variable refrigerant systems using variable speed compressor technology and also variable speed fan technology allow for effective riding of the building load, so the building only consumes that amount of energy at any given time of day, at any given time of year, local to each zone. And here's a graphic that illustrates the dynamic. There are two variable refrigerant technologies. There is heat pump technology, where condensers can be in either heating or cooling load, and you have to be careful on how you zone heat pump technology to make sure that you have the proper grouping of air handlers per condenser, depending on which zone in the building is getting the greatest load or seeing the greatest load. However, a little more energy efficient approach is to use heat recovery, where you can actually do simultaneous heating and cooling from common condensers. This is achieved by using a third refrigerant loop that actually deposits refrigerant to branch selector boxes that modulate refrigerant flow strategically to each zone's air handler, so it can provide either heating or cooling while modulating refrigerant flow to efficiently do so. And the types of air handlers that are utilized for these systems vary in types of product. They can be ducted indoor air handlers, so you can serve multiple rooms from a common VRV unit, or they can be cassettes in each zone, whether ceiling or wall mounted, so that we can actually strategically bring that refrigerant to each room where we have the greatest efficiency available to the greatest number of zones. So what about the ventilation air that we require to maintain a healthier environment? How do we deal with ventilation air and the outdoor air necessary for a variable refrigerant system? A conventional approach, certainly in Phoenix, Arizona, is to apply an outside air duct and tie it into the return air section of an indoor air handler, either a ducted unit or even into ceiling cassettes, so the system draws the outside air into the space necessary to meet the ventilation load. The minimum outside air requirements are defined by ASHRAE Standard 62.1, and 62.1 has been adopted by most local code authorities. So in looking at this type of system, let's look at the variable refrigerant indoor air handler component. If you're bringing untempered outside air and ducting it into a VRV plenum, so you get outside air distributed throughout a building, the total load of that building, including the building load and the outside air load, is seen at the cooling coils of the air handler of the VRV system. Well, in Arizona, this is an interesting phenomenon, because we have to be aware in Arizona when our peak summer design days are. I remember my earlier years in the industry, I used to think it was in June when it was 115, maybe even 120 we've seen more recently. However, our greatest load in Arizona, in Phoenix, Arizona, and in the Sonoran Desert, is during our monsoon season. If you look at the total energy, if you look at the sensible heat energy in the air plus the amount of water vapor in the air or humidity, the total load of a summer monsoon day is actually greater than a summer design condition within June at 115 degrees. Well, in Arizona, we see many times VRV systems used with untempered outside air, and it's understandable. It's to reduce the first cost of a design. However, these conventional designs are designed where the variable refrigerant system is designed to meet the peak load demand. And in order to eliminate thermal comfort complaints, we have to design to that peak load. Dehumidification, of course, for the outside air and the building moisture gain due to occupants, bathrooms, sinks, etc., occur at the indoor air handler cooling coil. Consequently, you have drain pans that begin to fill with water, and you have to have, in some applications, even condensate pumps necessary to drive that water out of the building so that it's not hanging in the pans and overflowing in certain design applications. If you have water in drain pans, however, there is a biogrowth concern that could impact building IEQ, and it will also add to some of the humidity load within your building. So if you design to peak load, be aware you start losing the potential energy efficiency in a variable refrigerant system, because at peak load, VRV systems are not altogether out of line with a high SEER package rooftop unit. VRV systems achieve their efficiency at part load when they can more effectively distribute refrigerant throughout a building to meet the various loads of the various zones throughout the space and avoid the start-stop cycling of compressors or package DX units that we see with more conventional designs. So the problem is that if you design a variable refrigerant system with untempered outside air and you size to peak load demand, higher outside air condition results in higher mixed air conditions at the air fan coil unit cooling coil. Higher mixed air conditions equal greater cooling coil total load. Greater loads mean larger condensers. So you have to upsize the condensers if you designed the peak summer load that you would need to do to condition the untempered outside air. So if you have VRV condenser capacities increased, what do you see? Larger and heavier condensers. Condensers that offer less turn down when variable refrigerant systems are most efficient, which is at part load conditions. You have larger condensers, you have greater first costs. And also the larger the condenser, the less turn down capacity you have, resulting in higher operating costs throughout the life of the system. So your system efficiency inherent in variable refrigerant technology is compromised. Just something as an aside to be aware of. If a variable refrigerant system is being designed using ASHRAE's Phoenix, Arizona, Maricopa County design guidelines of 110/69.5 wet bulb, only 0.4% of Phoenix's annualized hours see this peak load, 0.4%. So you're designing a variable refrigerant system to handle this load, compromising its part load efficiency during other times of the year. And by the way, most engineers design to 115 degrees. So if you're upsizing condensers to meet that ambient condition, your 0.4% annualized hours becomes even less. So is there a better way to approach these types of systems? And the answer is, I think there is, and I think we should consider 100% outside air VRV a hybrid design, where we decouple and condition the outside air independent of the variable refrigerant system. So the concept is to provide 100% outside air unit or dedicated outside air unit that only conditions the outside air. It is completely decoupled from the refrigerant system. One of the advantages of handling the outside air is you take care of the humidity of the outside air at the DOAS unit. It doesn't have to be addressed at the variable refrigerant indoor air handler. And then you supply load neutral air of 75 degrees that has been dehumidified. So we'll look at how you do that shortly. So if you can handle the outside air through a DOAS unit, you reduce the VRV system load and consequently reduce the condensing load of a fan coil, the fan coil cooling loads, resulting in less condensate at your VRV fan coil unit. So decouple outside air from the VRV system using a dedicated outside air system. Again, and to repeat, the outside air treatment through a DOAS unit is parallel and independent to the variable refrigerant system. Outside air is delivered directly and independently to each space, to each zone. You have enhanced energy efficiency by using heat recovery technology that are more often than not supplied with these units. And then as you dehumidify at the cooling coil of a DOAS unit by bringing outside air to dew point at 55 degrees, you use the heater rejection off of the DX circuit compressors, and you apply that heat of rejection to a reheat coil downstream of the cooling coil, so you can raise that temperature off the cooling coil back up to a load neutral condition of 70 degrees and consequently not have to pay a reheat penalty. So looking at 100% outside air VRV hybrid design, outside air is independently treated at the DOAS unit to a load neutral dehumidified condition. Lower entering air temperature at fan coil cooling coils mean that the VRV system sees a decreased load. Consequently, you have improved condenser efficiency. You can downsize the VRV condensers accordingly, and offering not only more efficiency and lower first costs, you also have the advantage of lower dimensional footprints in these systems. So a parallel outside air delivery to zones for enhanced system efficiency and assured IAQ is maintained and validated. You can actually regulate the amount of outside air a building owner wants to the space, whether it be code minimum as prescribed by ASHRAE Standard 62.1, or increase the air change rates with outside air to reduce the risk of infection even further, as ASHRAE's Epidemic Task Force guidelines recommend. And you can add another layer of improved IEQ with deeper humidity control. And we're going to demonstrate that here shortly. So 100% outside air, variable refrigerant concept. Let's look at an application. How do we apply this concept to an actual project design? Well, I was working with the Smith Group team on a project, and we thought that it would be good to evaluate, I thought it'd be good to evaluate 100% outside air system, 100% outside air variable refrigerant system for a more common building type, a building that has less square footage or medium square footage, buildings that we see more often than not as opposed to large institutional applications. So we looked at a common building, and we looked at a building design to enhance that would, the owner wanted to have enhanced indoor air quality because it was a medical office building. And so the building that Smith Group offered me to look at was a 28,000 square foot medical office building designed here for Maricopa County at 1,100 feet. The actual load calculations were generated by Train Trace. So let's look at the three design concepts for the medical office building we have under review to evaluate 100% outside air VRV solution. Design number one was a VRV system, and it was the primary HVAC system. It utilized untempered outside air mixed with the return air at the fan coil units. We applied a summer outdoor air condition of 97 degrees dry bulb, 78 degrees wet bulb, which is our Arizona monsoon design condition. We looked at a return air condition of 75 degrees at roughly 50% RH to conform to ASHRAE Standard 55 guidelines, and that equals a room or building dew point of 55 degrees. In the winter months, we designed to 38 degrees for this evaluation. Design number two was a variable refrigerant system with as the primary HVAC system, and then we provided the DOAS outside air system as the secondary unit. So we used 100% Daikin, 100% outside air Daikin rubble unit with an enthalpy wheel to precondition the outside air, and we selected the coil at a size that we could hit a dew point of 53.32 degrees, really, which is the leaving air condition of 55 degree dry bulb, 54 degree wet bulb. Design number three, however, we decided to take it a little further. We looked at variable refrigerant system with a 100% outside air unit that supplied lower dew point supply air. Why would we do that? And what advantage does that have to offer? Well, let's look at the findings. In design number 2, with the hybrid system of a variable refrigerant primary system with a parallel 100% outside air system, the cooling coil on the 100% outside air system was to deliver and designed to deliver and supply 55-degree dry bulb, 54-degree wet bulb air. That is air that equals a dew point of 53.13 degrees. What is dew point? Dew point is the temperature that forces water vapor to condense into water liquid. If you remove enough energy from the air, water cannot maintain itself in a vapor state and it condenses into a liquid. And that is known as the dew point temperature. So at 55 degrees dry bulb, 54-degree wet bulb leaving air temperature off the cooling coil, you have a dew point of 53.13 degrees. You then use a hot gas reheat coil that I referenced earlier to raise that temperature from 55 to load neutral 70 degrees while maintaining the dew point. Dew point, unlike relative humidity, is not dependent on temperature. Consequently, it's an absolute value. In design number 3, we decreased the leaving air temperature off the cooling coil of the DOAS unit to 52 degrees dry bulb, 50 degrees wet bulb, resulting in a 48-degree dew point temperature. Consequently, whether you're providing 70-degree load neutral air off the hot gas reheat coil or 55-degree air if you're in 100% cooling for all the variable refrigerant indoor air handlers, you can still maintain your dew point at 48.8 degrees. If you want to control building humidity, you need to control the dew point. If you're supplying air at 55 degrees through diffusers in a conventional system, and it's actually 55 degrees, and you're trying to condition and maintain a space at 75, 50 degree RH, it has a dew point of 55 degrees. You're running the risk of condensing on your diffuser. So it's very important we understand to control humidity, you have to control supply air dew point in relation to the building design dew point. Now, please be aware that these systems were designed using Daikin's Series 4X condenser. So for this evaluation, I wanted to make you aware that Daikin has since launched a newer technology that is currently available called a Marion. These condensers are very compelling, is because they offer, as my understanding, 30% greater efficiency than their previous Series 4 condensers. So, however, this was not taken into the energy evaluation that we built for the article and for this presentation because the performance curves for Marion have not been provided and uploaded into Train Trace, which is what Judy Peters of Daikin Applied used to evaluate the energy performance of these systems. So let's have some design clarifications as we move forward with our analysis. Room layouts of all indoor units and peak loads remain the same for all 3 design scenarios. Fan coil sizing remain the same for all rooms. Condenser capacities changed per design because the latent load changed depending on which design we used. And also be aware that the evaluation was done using TMY3 weather data, which ended in 2005. Studies have demonstrated that our current weather data has seen a considerable increase in temperature since 2005. So the values that we're going to see are very conservative values for energy savings. So I already talked to this point earlier about humidity control providing conventional HVAC systems. So using only a 1.83 dew point depression efficiency. So something to consider, and we'll look at that perhaps in another presentation. So as we're running out of time, let's just do a quick review of our findings of using 100% outside air VRV system in comparison to an untempered outside air solution. So if we look at a variable refrigerant layout using an untempered outside air system for a 28,000 square foot medical office building, we see that the VRV condensers see the total load, the sensible load, as well as the latent load in the building. Consequently, the indoor air handlers see full condensation of the latent component of the humidity at the indoor air handler. Consequently, condensate pans fill with water, and the VRV system is oversized in order to meet that peak summer design condition. If we look at decoupling the outside air from the VRV system sees only the zone total load. Consequently, the dehumidification load at the fan coil units are reduced. Fan coil the condenser sizes are reduced. Space humidity load seen at the indoor air handler is reduced. You have reduced coil condensation and deeper space humidity control. In looking at the VRV design, the VRV system can be downsized. The untempered mixed air system has a nominal tonnage of 105.6 tons because the latent and the sensible load is being addressed in the VRV system for both the outside air and the building. If you have a parallel DOAS system supplying 53-degree dew point supply air, you can downsize the variable refrigerant tonnage to 74 tons. And if you provide a low dew point for deeper humidity control DOAS solution, you can reduce the VRV tonnage to 64 tons or 64.8 tons. So what does that mean? Well, design number 2 offers a VRV tonnage reduction of 31.2 tons, and a 48.8 degree dew point supply air can reduce the tonnage of the VRV system by 40.8 tons. Consequently, what happens, and I remember having this discussion with Judy Peters when she did the energy analysis, and one of the comments she made when she did the evaluation for the low dew point DOAS solution was that the VRV system became predominantly a sensible cooling system, reducing significantly the amount of condensate that would form at the fan coil cooling coil unit. And this would also help us to avoid condensate pans with water and reduce the risk of biomass growth and its impact on building IEQ. What does it mean with regard to energy? Well, design system number 1 required 108,000 kilowatts per hour of annualized energy consumption. Design number 2, supplying 53.13 degree dew point air, had 87,972 kW per hour of consumption. And design number 3, supplying 48.8 degree dew point air, offered even greater efficiency at 80,104 kWh. And by the way, these values not only include the variable refrigerant system, but also the DOAS unit, including the fan energy in the DOAS unit was taken into evaluation for these numbers. So design number 2 offered 19% greater energy efficiency over design number 1, and design number 3 offered 26% energy efficiency over design number 2. What does that mean with regard to equipment first costs and payback? Well, let's have a quick look. If we look at the untempered outside air solution for design number 1, the variable refrigerant equipment alone, this doesn't include refrigerant piping or electrical or any of the supporting ductwork that is necessary, just the variable refrigerant equipment alone was $239,875. So the reason for this is because for this price is because you have larger condenser sizing, the condensers are heavier, and you also have a larger mechanical footprint, which could influence your architectural design. If we look at design number 2, we see that the system, including the DOAS unit and the VRV, is more money. It's $17,270 more to purchase the VRV and the DOAS equipment than it would the untempered system. However, we see a projected payback for a 28,000 square foot medical office building of 5 to 10 years. And since variable refrigerant systems are designed to last 20 years, not 10 to 15 years that current package DX units are currently built for, then if we look at the life cycle cost of the VRV system, there are some pretty compelling reasons why you might consider this first cost premium. What does the owner get out of it? Better building humidity control, enhanced system energy efficiency, the reduced risk of building condensation and biogrowth with coils, and the amount of outdoor air is strategically supplied to each zone to maintain indoor air quality and reduce the risk of infection. Design number 3 is a little more money because the DOAS unit to supply 48-degree dew point air has to be increased in size. Total cost is $266,000 at a premium of $26,000 and a payback of 6 to 11 years. However, in providing this deep dive in lower dew point temperatures on your supply air at 48 degrees, you can now control your building humidity between the 40 to 60% range advocated by ASHRAE and the CDC for reducing the risk of infections in buildings and creating healthier environments. We also allow for premium system efficiency as demonstrated by a 26% energy efficiency, and we can provide strategically the outdoor air necessary to each zone, and we can validate it. We can measure the outside air to prove that each zone is getting the outside air necessary in order to maintain building in zone IEQ. So concluding remarks, let's review the market forces that are driving us to reconsider how we do HVAC systems. We have, due to the pandemic, an awareness that we should know how to reduce the risk of infections in the built environments. We are becoming more and more aware of the importance of building IEQ and how indoor air quality impacts the physiology and health of occupants within a building. We looked at the pressures of the CDC, the EPA, and ASHRAE on what their recommendations are to increase ventilation and indoor air quality in the space by supplying more outside air. And then we're faced with the net zero initiatives for heightened energy efficiency and decarbonization and electrification. All of these pressures are bearing on the market today. So to span that divide, I suggest that we look at more closely 100% outside air 100% outside air variable refrigerant systems to span the divide that we have before us, to allow for enhanced energy efficiency, provide enhanced IEQ, to provide better building humidity control while offering premium energy efficiency on system concepts if we choose to evaluate them. Thank you very much for your time and consideration, and I'm sorry to go over. Well, actually, we're just a couple of minutes over, and I'm open for any questions. We've covered an awful lot of material.
Okay, so we do have a couple questions in the chat. As a reminder, if you do have questions, go ahead and type them in. So first, do we size the DOAS at greater than minimum airflow to follow ASHRAE and CDC guidelines for improved indoor environmental quality?
The answer is you can, absolutely. The problem is I'm not aware of any current studies being written to assess what is the optimal outside air design flow to reduce the risk of infection beyond providing just code minimum. There are some ASHRAE studies, and there is some research that demonstrates that 2 to 3 air changes per hour to each zone is better than our current design in order to more effectively flush out contaminant for a room. But I've even seen numbers of 4 to 6 air changes optimal for providing effective flushing of a building space. But I've not seen any validated studies that demonstrate at what air change rate result in the optimal indoor air quality to maximize the health considerations of an environment.
All right, so we have a couple other questions. Does design 2 and 3 total tonnage include the DOAS tonnage?
Yes.
That was an easy answer. I'm guessing this assumes regional.
Oh, well, no, wait a second. Wait a second. We looked at design 1, 2, and 3 on the variable refrigerant system with regard to the energy requirements that system needed to be designed to. The DOAS component was taken into account during the energy analysis portion.
Okay, so next question. I'm guessing this assumes regional higher humidity areas. I did not see any humidifier impacts or costs.
We did not incorporate humidifier impacts or costs in the study. It is certainly an option that you would want to look at because our driest time of year is during our winter months. Certainly in Maricopa, it's from November right the way through February. That's our driest time of year. And it would be easy enough to provide an adiabatic atomizing humidification solution into the DOAS component of a space and putting in a humidifier grid into the supply air from the DOAS ductwork. So if you wanted to maintain 40 to 60% humidity during our driest times of years, it would be an easy solution. But of course, there's a first cost impact for doing that. And there's a maintenance component as well to make sure those systems are supplying the moisture required to maintain those humidity levels.
Okay, so Brandon asked that question in Albuquerque, so I don't know what their humidity is like there. And I know you were talking about our monsoon conditions, which in Phoenix gives us the humidity. So maybe that's where the question came from.
That could be, but even I've got a presentation on humidification that demonstrates we don't really have all that dry of a condition in Phoenix in June. And our driest times of the year by far are in our winter months. And I know it's somewhat counterintuitive, but I've got the numbers to demonstrate that fact, and maybe we can do a humidification webinar sometime in the future.
All right, and Alan just said that we are much drier in the summer and winter. Those are the only 2 seasons we get in Phoenix. So
that's for sure.
Next question: how are you handling winter operation and humidity control? Okay, so that's kind of back to the same question. I don't know if you need to.
That's an excellent question. Again, it depends on the building type of usage, what type of building humidity is being generated by occupants and building usage, sinks, restrooms, etc. Anywhere where there's open water to the environment. The best way to actually deal with that, depending on the building, is you're going to need some way during those drier times of the year in the winter of providing humidification or moisture to the space so you could control to 40 to 60%. Otherwise, you can see it drop below 40%. And by the way, I don't think it's any accident that our cold and flu season is during the driest times of year. So just something to keep in mind. But a supplemental secondary humidification solution would certainly be necessary in Phoenix.
All right, and sounds like Albuquerque as well. That is all the questions that we have in the chat. So if you do have questions, you can go ahead and add them still or jump off mute if you want. Just a reminder, if you are still on here, open up your chat and see if you have a message from me. Because if you have a message from me, it means I couldn't figure out what your name was to give you PDH credit if you needed it. So please do check that before you jump out of here, and kind of wait a few seconds if anybody has any other questions. All right, Davin. I don't know if you want to type it in or come off mute.
Can you guys hear me?
Yes.
Yes.
Okay, so with that, as far as all the data that is shown, does that reflect how buildings are designed as far as insulation and how they are built?
And the answer to that question is yes. ASHRAE Standard 90.1 offers directions on how the architectural features need to be built. For example, Standard 90.1 2019 now has written into its documents that vapor barriers will be provided for all perimeter walls in buildings. That'll allow for deeper humidity control for future buildings, certainly during the wetter times of year. So it also gives various other architectural design guidelines. ASHRAE Standard 90.1, though it deals with mechanical systems, also offers guidance on how architectural features should be built to provide enhanced performance of buildings.
And that will be different depending on different regions of the area?
No. Well, yes and no. The standard is the standard. What each municipality adopts from the standard varies depending on what that municipality decides on. The local code authority in the end has jurisdiction. The standard is a guideline. It is the standard. And then what local authorities take from the standard is up to them. The Department of Energy has issued each municipality up to 2 years to evaluate and incorporate the language of Standard 90.1, 2019. I'm confident there'll be challenges and whatever going on with various cities and states on to what portions of the standard are being adopted within the municipalities. And I think it's going to go on for some time, but the Department of Energy issued a 2-year window. It's going to vary per city.
Okay, thank you.
Sure.
All right. That's all our questions. So as a reminder, I will send out an email after this with the PDH credits. If you requested it, we'll get your AIA stuff entered into our system if you requested that, along with a link to the video of this recording and to the website that I showed at the beginning with all of the supplemental documents and the library full of all kinds of resources.
So Kelly, thank you. Thank you again, all of you. Please. What we learned at the Why Buildings Matter Symposium is the interest in generating dialogue between engineers, architects, owners, contractors, or whatever, and how high-performance building systems work. That's the purpose of the Varitec Technical Institute and for the website and the web page that Kelly has designed. We want to be that resource. We want to listen to you and hear what your concerns and needs are, and make sure that we take that into consideration for future presentations.
Absolutely. Thank you so much, Dan. And thank you everybody for joining us.
Thank you.